Okay, so yesterday we talked about the bacteria growing, and just to recap this example, actually, we said the initial amount of bacteria, you don't even have to calculate that, that's right in the front of the equation. And the growth rate of the bacteria is pretty obvious, it's right there, it's 0.04. And the population after 3 hours, remember we found N of 3, so we literally plugged in 3 for time, and I think we got 112.7 bacteria, but we rounded it down, right? Because we didn't believe a half a bacteria counts, or 0.7 bacteria. And then we calculated when it would reach 1,000. We actually did that by putting 1,000 on the left. And then we left this as 100 e to the 0.04 t. And we found that to solve this, you can actually go really fast. Watch this. To get t, you can do it all in your head. First thing you would do is divide by 100. Then you would obviously get 10. And then you would ln it. That would get rid of the e. And then you're going to divide by 0.04. So we saw that you can actually go really quickly through this process just by doing ln of 1,000, that's the new amount, over 100, that's the initial amount, all over the k value. So I encourage you to jump straight to this. And I think this came out to 57 or something. You guys have the number still?
Yeah. 57.56.
So we'll say 57.56. Sounds like the right number. This is hours. Okay, and then we said, how long will it take the bacteria to double? And listen, if it goes up 10 times the amount in 57.56, you cannot just assume that it's going to go up double in a fifth of that time. It doesn't work like that. It's not linear, you know. So every year I have a student or two who say, well, I did part D, I think I can figure out part E, I'll just do 1/5 of the time, because it's only going to go up double instead of going up 10 times. Can't do that, okay? You need to recalculate it. But you could use this pattern here. You could just use t equals ln of 200 over 100 over 0.04. In other words, final over initial. That'll work. And this came out to be what? 17 point what? 33 hours? Okay. So you don't have to recalculate everything, but you do have to stick to the formula. Don't just use some crazy, like, linear, like don't use a proportion. Don't solve by proportions. Okay? Every year someone does that. Let's go on to decay now. So I want to show you, oh no, we have to do this one, I'm sorry. This one is, this one's a little more cryptic. Okay, so this problem starts off with some givens in the instructions, but they're not the most desirable givens. Okay? Here's what I mean. They told you that there were 20 bacteria, right? So that means it's going to be 20 e to the kt. They told us that this is going to turn into 212 bacteria after 12 hours. So it looks like you're going to have to basically write a 212 on the left, and then you're going to have to put a k times 12 hours up here. So this is not the most desirable given set. I wish they'd just given me k, but they didn't. So it looks like that's our given. Okay, so to solve this, you would divide by 20. You would then ln, and then you would divide by 12. So you're going to be able to get the k. You're just going to have to do ln of 212 over 20 over 12. Okay, so let's get the k. What is the k value? I need ln of 212 over 20, all divided by 12. I'm getting 0.1967, yada yada. And I think we should store this as k in our calculator memory. So let's do store as alpha k. So I'm going to store it in my calculator memory. Did I show you guys how to do that yet? Recently? Okay. It's pretty easy. You just press STO and alpha k. All right, that way I'll never have to type that number again. And let's go to the question now. Part A says, how many bacteria will there be after 24 hours? So you're going to go, the number of bacteria will be the starting amount times e to the k t. T is 24 hours. And when I actually type this, I'm just going to type 20 e to the 24k. That's what I plan on typing. So I'm just going to type 20 e to the 24k. It's all super accurate. It's 2247 to the nearest, 2247 to the nearest bacteria. Okay? How long does it take the bacteria to increase tenfold? Do you guys know what tenfold means?
10 times.
10 times its original. Okay? Listen, we just did this problem back on the previous example, part D.
You can't multiply it.
So I'm just going to go like this. Watch. ln, starting amount, over, actually, final amount over starting amount. All over k. And since my calculator's already memorized k, this will give me my double, my tenfold life. That's what it's called, tenfold time there. So, in other words, you could just type ln 10. Just type ln 10 over k. And k is already stored. So 11.70. And this would be hours. It's a time. If you're not comfortable using shortcuts like I just did, that's fine. Just set up the formula at the top of the board. At the top of your page, just set up the formula. Plug in 200 for the final, 20 for the initial. K is known, solve for T. I'm just trying to get you through it a little faster. All right, let's go on and talk about decay. So not all things grow in nature, right? In fact, my money doesn't even grow. My money seems to decay. After all this talk about money growing, money seems to be decaying. Although my debt's not growing, that's good. But some things naturally decay, right? Like if you put a pile of carbon-14 on a table, it would slowly decay back to carbon-12, which is the stable version of that element. Or if you had uranium-238, watch out, dangerous stuff, right? It would eventually decay back to its stable and safe form, U-235. Okay? But it takes a very, very long time for that to happen. And this formula that we've been using for money and bacteria works here as well. So it doesn't matter what kinds of formulas your science teachers are teaching you. If they're teaching you formulas like n equals n times 1/2 to the t over h, just throw that in the trash can. This guy right here, this is your friend. If you memorize your teacher's formulas, okay, from the other classes, you might get them done faster, but if you use this, it works on anything. So this is more versatile, and it might take you 2 steps, kind of like the last problem to me, but at least you don't have to memorize the formulas all the time. Okay? All right, so this thing is really, really powerful. Here it is again. The only difference is this time they're not using n and n naught, they're using a and a naught, but it looks exactly the same as what we just had. And k is negative. That just means the growth rate is negative. It's not growing. It's dying off. Okay, so let's take a look at this example. Can you tell from the question what K is? It says, suppose a certain radioactive element decays by 8.7% every day. Can you tell me what K is just by looking? Negative, good. 0.087. That's it. Pretty simple. Okay, we got our K. That means we've got our model. So A, after 10 days, would be, starting amount was 100 gram sample, e to the k t. We're waiting 10 days. All right, time to get out the calculator. So how much of a 100 gram sample remains if it's been decaying for 10 days? Let's find out. I'm getting 41.90 grams remains. So I guess this element, whatever it is, if you wait 10 days, it'll drop from 100 grams of radioactive substance down to only 42 grams of radioactive substance. Okay, let's go to the next question. When will 30 grams of the sample remain? That really should say, when will 30 grams of the sample remain radioactive? Okay, so I don't want you to get the impression, let's say that this is like the new element called S234. Let's do S239, short 239 element, okay? It's not like this is sitting on a table and then it's just disappearing, okay? It's not like that. It's just the part of it that is unstable is diminishing. So the same lump is just sitting there. You can't see it disappearing. But the atoms in there, which some of them have too many electrons or whatever, or too many protons, those ones, they're all decaying back down to a stable form of the element. So it's not losing mass really, maybe negligible amounts, but it's just kind of a lump and it's becoming less radioactive. Okay. So this should say how much, when will 30 grams of the sample remain radioactive? Anyway, you just use 30 for your final amount. That's on the left. See? And then it was a 100-gram sample. E is here. There's your K. We don't know T. But look, we're going to isolate very quickly. Divide by 100. Ln. Divide by K. So you can just type this. Ln of 30 over 100 divided by the K. This will give you your time. Okay? So take your time if you need to go from here to there, but I've got it down to where I can do it quickly in my head. All right, let's try it. Ln of 30 hundredths divided by 8.087. Looks like 13.84 days. All right, what is the half-life of the element? So scientists make a really big deal of half-life. There's nothing special about half of it remaining. You could ask the question, what is the 9/10 life? In other words, how long does it take for 9/10 to remain radioactive? I don't know why half-life is such a big deal. Okay, but that's kind of a common question, so let's go ahead and oblige it. We'll put 50 equals 100. Why did I put 50 right there? I wanted to know when 50 will remain. When will 50 grams remain radioactive? So I just put a 50 there because I wish to study half-life. So you basically just solve this for T now. You divide by 100, you ln both sides, divide by the K. So this is going to give you T equals ln of 50 over 100 over negative 0.087. In other words, ln of half. So if you look through a biology book, or like even a chemistry book or a physics book, you will see all these little fancy formulas for like this is the half-life formula, and this is the K formula, and all this stuff. Listen, it's just all about this right here, plugging what you know and solving what you don't know. See what I mean? Like, you don't need a bunch of formulas. There you go. I use that for everything. And I've got my half-life. I didn't have to memorize the half-life formula for that. Okay. So now if you go online and you find a half-life table, you might figure out what element this is. What half-life table? What element has a half-life of 8 days? I don't know. Or maybe there is no element. I kind of just made this example up. So. All right, let's go on. And now we're talking about Newton's law of cooling. So if you look closely at this law, this is significantly harder looking. If you look at that horrible law, well, the good news is I will give you this on the exam. Okay, I will put this right on the test. Okay? The bad news is I will not have the description. So you'll have to know still what everything means. Okay, so let's talk about what the variables mean. This is the temperature of the surrounding environment. This is the starting temperature. So T here, I'll just label it. T is the constant temperature. It says below there too. The constant temperature of the environment, or you could say the medium, surrounding medium. The U naught, that right there, is the starting temperature of the object. And this formula will calculate U, and U is the final temperature of the object. Final temperature of the object. Okay, the idea is really simple. Okay, let me explain it. Let's say that it's Thanksgiving Day, and sitting on the table is a turkey. So I want to try to draw a turkey now. This is the second turkey I've ever drawn. The first one was last period. Okay, so the turkey sitting on the table just got out of the oven. Okay, the turkey was 450 degrees, just came out of the oven. So it's actually 450 degrees right now, don't touch it. Sitting on the table. The temperature of the room is the capital T. Okay? Notice it shows up twice in the formula. U naught is 450. That's the temperature of the object. And I don't eat my turkey until it's 100 degrees. So I would put a 100 here and hopefully solve for T to figure out when I can eat my turkey. Okay? Or here's another scenario. It's not turkey, it's maybe an ice cube. Okay? So there's a plate on the table, and I don't know why, but there's an ice cube sitting, let me draw it in blue. A blue ice cube sitting right here, right on the table. There's a big ice cube. The T, the capital T is still the temperature of the room. Okay? U naught is probably 0. It's an ice cube. Just came out of the freezer. See? So we're waiting for it to heat up. But it doesn't change the scenario. This is a cold object in a warm room. The last example was a hot object in a warm room. Doesn't matter. The law is the same. Newton's law. You can use this formula to figure out when will the ice cube reach a certain temperature. Or when will it all reach room temperature. Or something like that. Okay, or maybe it's a cup of hot chocolate, which is what my example is about actually. Let's say it's a cup of hot chocolate sitting on a table, and the drink is hot, too hot, so someone throws an ice cube in it. Okay, now I got to be careful. Capital T is the temperature of the surrounding medium for that ice cube. Okay, so the capital T then here in this problem would be the hot chocolate, right? And the lowercase, the U naught, that thing is going to be the temperature of the ice cube when it first starts. Okay? This one's kind of a complicated scenario. You've got a hot cup of coffee in a warm room that's cooling off, but the ice cube is in the hot drink warming up. So there's you might need to do the law twice or something to figure this one out. But my point is to show you that capital T is the surrounding environment's temperature, and that U naught is the starting temp of the object. Okay, so my actual scenario problem here is Mr. Shore won't drink his hot chocolate until it's 130 degrees Fahrenheit, but the store sells Shore his hot chocolate that's 160, so I can't drink it. I got it, but I can't drink it. It's really frustrating. Okay? So I, of course, carry a thermometer everywhere I go. There's an app for that. And, I don't know. I just put my phone in hot chocolate. I wait 5 minutes, I check the temperature of my hot chocolate, it's still 140, I can't drink it. So I'm like, how much longer do I need to wait before I can enjoy my hot chocolate? So that's the scenario, okay? So let's just draw a quick picture. Here's the drink. The time is 0. The hot chocolate is 160 degrees.
Don't you have to know the temperature outside?
Yeah, I'm going to tell you in a minute. Okay, 5 minutes have elapsed. Now the temperature, I'm using U for temperature. The temperature is 140 degrees. See? What time will it be when the temperature is 130 so I can drink it? Does anyone care to guess at what time I might be able to drink my hot chocolate? Anyone care to guess? 7 minutes? 10 minutes? 7.5? It's 8.11, as we'll see in a minute. Ah, it's over there. Oh well. It's not on the video, though. So, yeah, we'll actually find out that it's 8.11 minutes. In other words, I need to be patient for another 3.11 minutes. That's going to be the answer to this question. All right. So how do you solve this problem? Well, you want to set up this formula actually twice. The first time will be during this first phase right here. Okay, so between these two temperatures, all right? So what happened between time 0 and time 5? Here's what happened. The temperature reached 140 degrees. Now let's assume that the room temperature here, Mr. Shore's version of room temperature is 75 degrees. That's my favorite temperature. So we'll just let room temperature be T equals 75, okay? So what happened during this 5 minutes? The temperature dropped to 140 from 160. So you set up all the numbers like this into the formula. And the time was 5 minutes. Okay, so I'll circle that one. So I did the best I could. I set up everything I knew about the first 5 minutes. I know the temperature of the room was 75. I know it was at 160 and ended up at 140. And I knew the time was 5 minutes. I should be able to get K from this, right? Okay, so first thing I'm going to do is subtract the 75. Then I'm going to divide by this 160 minus 75, which is really just 85. Okay, so you're going to have basically subtract that over, divide by this 85, ln both sides, divide by 5. Why don't you guys try it real quick? I'll pause the video, see if you get what I got for K. Don't be surprised that the K is negative, because the coffee's cooling. It's also on the board. Okay, thank you. Thank you very much. The K turns out to be negative 0.0537 after a bit of work. And see, now I can talk about this next time interval. Okay, so now I'm going to study this time interval here, and I need to set up the law all over again. Okay, so this time the ending temperature will be 130, and the starting temperature in this 75-degree room is 140, so this is a plus. 140 minus 75 times e to the kt, but I now know K, right? So this is my phase 2 calculations. I want an ending temperature of 170. If it starts at 140 in a room of 75, and let's begin isolating. So we subtract the 75, which gives you 55. Then you divide by the 85 again. So you find yourself in this situation. T is approximately equal to ln of 55 over 85 all over the K. Yeah, 65, yeah. Yeah, so we're going 130 minus 75 is 65. No, it's
No,
not.
it's 55.
I have 55.
It was 65 before,
Okay, so I'll fix it here. So this fraction should be 55 over what? Over 65, thank you. Okay, yeah, so you've got subtraction, division, ln, division. So what did it turn out to be? 3.11 minutes. So I need to wait another 3.11 minutes. In other words, when the time is 8.11, after I bought my coffee and waited 8.11 minutes, I can drink it. That's a long time. I meant to say hot chocolate. Did I say coffee? Okay. Does everyone understand this problem? Pretty powerful little tool. Newton's law of cooling. I'll give you the law on the test, but you have to know what all the letters mean. Okay?
Will this be on the quiz?
Haven't decided yet. Is it hard? It's open notes, right?
Yeah.
I might. It depends on how long the quiz feels. I don't want it to be too overwhelming. Okay, the last thing we need to talk about is logistic growth model. Okay? This looks so complicated, but the good news is in pre-calculus, right, the more complicated the phenomenon, the simpler the questions. Remember I told you that before. You get this horribly complex phenomenon, but then they just give you an equation, and then the questions become very like, here, plug this number in. Because they know you're not maybe comfortable deriving these formulas or whatever. If you take my BC calculus class next year, I'll show you where this formula came from, and you'll derive it yourself. Okay? Logistic growth. So what is logistic growth? Maybe you've heard of it. This is the case where you put the bacteria in a petri dish, and it starts to grow. It doesn't grow in its size necessarily that much, but it's growing in its amount. and it's growing, and then all of a sudden, it starts dying. Why?
Because.
Old age, environmental issues, right?
Carrying capacity.
Carrying capacity, maybe the petri dish isn't big enough to support 48 billion bacteria. Or maybe there's not enough nutrition for all of them, right? So while some are reproducing, others are dying, see? And so what happens is the growth appears uninhibited at first, but then it kind of peters out and reaches a theoretical maximum, right? So this is what happens with human population too, right? Humans reproduce, we have more babies, but at the same time people are dying. In fact, there aren't even enough resources to support uninhibited growth of anything in the universe. Nothing can grow forever, right? It's just not available. So we have a theoretical maximum. I wonder what the theoretical maximum is for human population of the Earth. 10 billion? I don't know. Never really thought about it. But listen, the formula is fairly complicated. The E is on the bottom, okay? And this number on top is super significant. So I had to pick A, B, and C, and I decided to put C on the top because it actually means carrying capacity. That's your theoretical maximum. Okay? Everyone with me? Okay. So this up here is the only one you have to know the meaning of. Again, on the test, I will give you this formula. You just have to know that this is the carrying capacity. I'm going to put max capacity, even though it's technically called carrying capacity. That way you'll remember what it means. Okay, so how hard is this problem? It's not very hard. Let's look at it. This is a problem about, and I'm going to say bears on an island. And you only have 4 parts to it, so I added a 5th part. The very first question is new. So why don't you renumber your A, B, C, D as B, C, D, E, and squeeze in this part A, what is the initial population? Okay? Please do that. Take a moment, write in what is the initial population. You guys have A, B, C, D, but up here on my projector, those are B, C, D, and E. So this is a new question. Squeeze this in there if you can squeeze it in. Thank you. Okay, what is the initial population? That just means let t equal 0. And let's see how many bears were on the island at the beginning. Okay, so that's a false alarm. Bell's got 5 more minutes. All right, so we're going to plug in 0.
Please excuse the interruption. Attention all students to take the
Okay, you're going to plug in 0. So watch how easy this is. You get 560 over 1 plus 92.33 e to the 0. E to the 0 is 1. So it looks like we're just basically dividing 560 over 1 plus 92.33. In other words, we're dividing by 93.33. So I typed this into my calculator, and it came out to the nearest bear, 6. 6 bears. So we're just pretending it's bears. Okay. What is the carrying capacity of this island? 560. Look at the numerator. See that? That's not a calculation. That's trying to understand the formulas for today. So the top number is your maximum population. What is the population after 5 years? Well, I need to find P of 5. So I actually typed this on my calculator. 560 over 1 plus 92.33 e to the negative 0.185 times 5. And I was very careful to type it properly. And I got 14 bears. Good, good. When will the population reach 200 bears? Well, that goes on the left side, see? And now the time is unknown. You can use the solve feature to solve for t if you have a TI-89. Yes, you can. But ultimately, remember the old trick? You can switch these around. So you can move the 1 plus 92.33 e to the minus 0.0815 t over here and put the 200 down on the bottom, right? Okay. So it's going to be 560 over 200, which is 2.8. So now this leads us, I'll do this in blue. So this just leads us to 1 plus 92.33 e to the negative 0.0185 t equals 560 over 200. And the rest is pretty easy. You're going to divide 560 by 200. You're going to take away 1. Right? you're going to divide by 92.33. Then you're going to ln. Then you're going to divide by the negative 0.0185. And you get 212 years.
212?
Is that what you got? Did anyone else get that? 212 years. How long will it take to reach half the carrying capacity? Same question. Just put a 280 here because that's half of 560. Solve it all over again. Or ask Jack, he's got the TI-89. I want to say it was 200. I'll put the number in if you wish to see it. I think that it's 24.46 years. I'll check it later. Yeah. So I'm off by 1 decimal. This is 244.61 years.